come get him, he's gonna be like, why'd you put that? That's not.
That's his tea. Anyways, so look how much time you're missing. All that you could see just by not doing that. And that's how Thursday I'm gonna be done for you because you're gonna be sitting over until the shit. And I'm gonna be like,
I'm on Thursday.
what?
Not on Thursday.
I haven't looked at it. Mr. Randy's structure.
I'll try to.
I was wanting to.
I'll try to look for it. Are you still working on the canoe?
Yeah.
Even though we're like running late?
Same thing.
You're the only one that knows.
Don't forget seed materials.
We have seed materials on it?
Yeah, you know. Let's do one seed. I think one seed. Yeah, one seed.
So the ASUCE.
Any work?
Yeah, so not so well.
At work?
Pretty much. That's when I got the sign county.
So how much you make on this end?
About $4,000.
I should have told you coming up to what you had to shoot this for.
I made $100.
Yeah, that's $100 more now. That's all you
I
made.
made 120 and I tipped out Kitchen Reggie another guy. I don't always do. I'm not sorry. And then I had to tip.
I don't care. I'm not.
I sold 3 bar drinks and I had to tip out for
I probably will never.
$1,100.
Just get you just because of my big leagues. They're gonna argue with me over fixing something when I'm picking out.
I always tip my parties.
Who gets the money? Do they split that $2? 6 legs?
The only person that doesn't get it, who I'm actually tipping out, is JD, because he's the one that is making my food. Is that why y'all stayed for Kyler's smashing?
I was going to, but then he still took his up something.
Yeah. He got pissed. It's like, run his pretty little hair.
Did you get all over it?
Yeah.
The bitch knew it was coming on the line.
Oh, he did?
Everybody on the list has.
Yeah. But I didn't know if he had been there for the end.
He put it up for 2 of them, Morgan's and what's his name?
I need this to go pending. Quit saying that. It's pending. Indeed. Yes. You need to what? You need Patrick's hairs and then it's
There's a rank right beside 501.
Yeah. Was there Yeah, because I had to go through the damn skating parking lot.
Those are nice little schools.
Sorry. Busy. everything that I'm paid to get that licensed. I had to pay for my classes. I had to pay my NLS dues again. And think probably around $900. And then I run off all the gas.
Wow. Tardy.
Is he?
You're late. It's 9:31. Class is canceled out.
Where is everybody?
Yeah, where is everybody? Homework's due today and no one's here.
That's why.
I guess, yeah.
That's dumb.
I didn't get the homework done. I'm still
So where are you going next week?
Conference in Pittsburgh.
For where?
Hmm?
For what?
Conferences for what?
Yeah.
Mechanical and mechanics.
Why are you going
Why?
to mechanical and mechanics?
Because I'm in mechanics. All that I'm teaching is mechanics. This is all mechanics.
So is it just you going or other professors you're going to?
Yeah, let's talk about you today.
Is it-
David from mechanical engineering, he's going as well.
Jean?
Yeah.
Like the not man Jean, not lady Jean?
Mel
Yeah.
Joe.
Male Jean?
Dr. Ron's not going?
I'm like, why is it lady Jean?
Yeah, but her forte is environmental art.
So your kids stay here, I'm assuming?
Yeah.
I bet you can't wait to get a week off from the kids.
You're not nice.
What do you mean?
So
Can we have a review day since no one's here?
they're gonna come.
They're gonna come?
Yes.
Oh.
Straight.
Okay, so good morning, everyone. Today we're going to start a new chapter, matrix structural analysis, but for frames. And that's chapter 16 in your textbook. Okay? So, so far we covered chapter 14. We started actually with the chapter 15 for the beams, okay? And then we extended that to chapter 14 for the trusses. So what was the difference between the going from beams to trusses? It's the same method, it's the same steps. The difference is the stiffness matrix looks different, and the beams, all the elements had the same direction, so we didn't care about the direction, right? While for trusses, you had elements or members with different orientation, so we introduced that new concept, going from beams to trusses. We introduced that concept of the local matrix and the global matrix, because not all the elements have the same direction. While for beams, the local is the global, right? They are all in the same direction, so there is no necessity or need to transform or have a matrix in a local direction and a global direction. While for trusses, definitely we have this need, okay? Now, moving forward to frames, we're still gonna follow the same steps. It's the same method, okay? But the differences will be what? the stiffness matrix for the frame element will be different from the beams and will be different from the trusses, okay? So it's all about, having that, different element stiffness matrix for each of those members. The beam had the stiffness matrix, the element had the truss had a different stiffness matrix, the frame is going to have a different stiffness matrix, okay? And to do this, we first need to know what are the degrees of freedom, okay? So in beams, per node, how many degrees of freedom we had? 2 in beams. They were the vertical displacement and the rotation. In trusses, we had 2 degrees of freedom, which is vertical and horizontal displacements. The rotation was not a degree of freedom, okay? So in frames, what do you think? How many degrees of freedom would we have in a frame node?
I would say 2.
2? No, there are going to be 3. A vertical, horizontal, and the rotation, okay? So it's a combination of the beams and the truss, okay? So it's just, a combination of both of what we learned so far, okay? So let's write here, the differences that we're going to have. So for frames, so the method is the same, okay? But let's see. For frames, okay, let's list the differences. First, we need to know what are the degrees of freedom at each node, okay? That might be, or that will definitely be different. And then the other thing that is different is, again, here also for frames, elements will have different orientation, right? So we're sure that there will be local direction, or local coordinates, and global coordinates, okay? How to transfer from the local coordinates to the global coordinates, that's the difference, okay? So what is the local stiffness matrix for a member? And once we know this, what is the local stiffness matrix for a member, what is the global, how to transfer from that local stiffness matrix to the global direction, to the global stiffness matrix. And then to do this, to transfer from the local to the global, you definitely need to know what is the transformation matrix. So let's do this one by one. The first one here. We're talking what are the degrees of freedom at each node. Okay? So a frame member, the general case here for a frame member, you have the near end and the far end. Okay? So at each node here, okay, you're going to have 3 degrees of freedom at each node. 3 degrees of freedom at the near end and 3 degrees of freedom at the far end. What are those? A displacement in the x, a displacement in the y, and a rotation. If I use capital, that means that those degrees of freedom are in the global direction. So here I have a u, x, n, a u, y, a displacement in the y direction at the near end, and a rotation, theta, at the near end. Okay? And similar, 3 degrees of freedom, similarly 3 degrees of freedom at the far end over here. So u, x at the far end, u, y at the far end, and a theta at the far end. So that means since we have 3 degrees of freedom at each node, so therefore, for a frame member, how many degrees of freedom will we have? 3 degrees of freedom per node. How many nodes do you have in the member? 2. So how many degrees of freedom you have for the member? 6. Okay? So you're going to have 6 degrees of freedom are allowed for each member. Okay? Those 6 degrees of freedom that we just drew, okay, are in the global direction. Those are in the global direction. Okay? What about the degrees of freedom in the local direction? In the local direction, of the member, we're still going to have 6 degrees of freedom. So we have 6 degrees of freedom as well. But how do they look like? You're going to have here at the near end, you're going to have a u xn, but this is small x, okay? And u y n, okay? Those are in the local direction of the member. An axial displacement, uxn, in the direction of the member, a vertical or a normal displacement, uyn, and theta. Theta is the same here. There is no change. The angle of rotation doesn't change. Whether you're measuring this angle of rotation with reference to the global axis or the local axis, it won't make any difference. Right? Do you understand this concept? An angle of rotation is an angle of rotation. Whether you're measuring this from this local direction or from the global direction, the angle of rotation is the same. If it rotates by 2 degrees, it rotates by 2 degrees. Whether you're measuring this in regards of the global axis or the local axis, it's still 2 degrees. Okay? So there is no difference here. And theta f over here. So here at the far end, those are the local displacements, uy f and uxf. So whether you're finding your degrees of freedom in the local direction or the global direction, you have 6 degrees of freedom. Okay? In the local direction or the global direction. Okay? So in the local direction, you have 6 degrees of freedom. Those are the ones colored in green here. Okay? So that's the answer to the first question. Okay? What are the degrees of freedom at each node? We have 3 degrees of freedom at each node. The vertical, horizontal, and the rotation. That means that the stiffness matrix for an element will be how big? 6 by 6. You have 6 degrees of freedom per element, okay? Per member, so it's going to be 6 by 6. So the stiffness matrix for a beam member was how big? It was 4 by 4. The stiffness matrix for a truss member, how big was that? Okay. Before answering this, you should ask me, what stiffness matrix are you asking for the truss? Are you asking about the local stiffness matrix or the global stiffness matrix, right? For the truss, the local degrees of freedom, we just had 2, okay? So the axial displacement at the near end and axial displacement at the far end, okay? So for a truss member, the local stiffness matrix is 2 by 2, but the global stiffness matrix is 4 by 4, right? Now, for a frame member, how big is the stiffness matrix? In the local direction or the global direction? It's going to be 6 by 6 in the local direction, and it's going to be 6 by 6 in the global direction, okay? But they're not going to be identical, okay? They don't look the same, but the size will be the same. It's going to be 6 by 6 whether you're using the local axes or the global axes. Okay? For the truss, no. For the truss, in the local axes, it was just 2 by 2. In the global coordinate system, it was 4 by 4. Okay? So now, to answer those questions, what's the local stiffness matrix for a member, what's the global stiffness matrix for a member, and what is the transformation matrix, we can answer this question. And to answer this question, we need to find the transformation matrix first. Okay? So let's go ahead and write here the transformation matrix. Okay? So let's start by answering this question. What is the transformation matrix? So what is the transformation matrix? You remember we did this in trusses, so the concept is not new. The transformation matrix is where you have U small. What's U small? It's the local displacements, or the displacements in the member in the local direction, is equal to the transformation matrix. Okay? There is some matrix here that transforms this to the global direction, to the global displacements. Okay? So here, for example, what are the local displacements for the element we just do? You had a U xn, a uyn, a theta n. Okay? A ux f, a uyf, and a theta f. That's the arrangement that I'm using here. The horizontal and vertical displacements, and the rotation at the near end, and then horizontal, vertical, and rotation at the far end. Okay? This would be equal to some transformation matrix over here. This is 6 by 1, right? Let me try to give myself more space here. Okay? Even more space won't hurt. And then this is multiplied by U capital, the displacements in the global direction. What are the displacements in the global direction? U x capital, okay? The displacement in the x, in the global x direction at the near end. U y capital, the displacement in the y direction, the global y direction at the near end. And then theta n. U x uppercase at the far end, U y uppercase at the far end, and theta at the far end. That's 6 by 1. So what do you think, what's the size of this transformation matrix? It's going to be 6 by 6. Okay, first, let's see here. We said theta m and theta f are the same in both coordinate system, the local coordinate system or the global coordinate system. There is no difference in theta, right? So that means that this theta m is equal to that theta m. There is no difference. That theta f is equal to that theta f. So how would you make those equal to each other? This is going to be 0, 0, and then 1, 0, 0, 0. Right? This theta n is equal to this row multiplied by that column. So 0 multiplied by this, 0 multiplied by this, 1 multiplied by theta n gives you theta n and then 0. Okay? That way there is no change here. Okay? And the transformation matrix should be symmetric, so those are going to be zeros as well. We need this theta f to be equal to that theta f. The theta f in the local direction is equal to theta f in the global direction. There is no change here. So how to do this? You're going to have a 0 here, 0, 0, 0, and a 1 here. This sixth row has to be symmetric to the sixth column. So those are zeros as well. So this is how you transform from theta n in the local direction to theta n in the global direction. Theta f in the local to theta f in the global. No difference, the same. Now, to transform those displacements from the local direction to the global direction, we need something similar in the trusses, okay? So this is going to be similar to what we had in the truss, CS, okay? So just CS over here, okay? And here's going to be negative S and C, okay? And definitely there is no relation between the displacements at the near end with the displacements at the far end, so here this part is going to be 0. And definitely there is no relationship between the displacements at the far end with the at the far end with the near end, so there is no numbers here. It's going to be zeros. And then it's symmetric over here, so CS, negative SC. What's this? This is the transformation matrix that you have for frame member. This is how, those are the numbers, or this is the matrix that transforms your displacements in the local direction to the global direction or vice versa. Okay? That's the transformation matrix that you need to transform the displacements from local to global or from global to local. Okay? Now that we know this transformation matrix, we answered that question. That's the transformation matrix here, okay, for the frame. Now, let's go ahead and try to find an answer to that question. That's straightforward. What's the local stiffness matrix for a member, for a frame member, okay? So let's copy this and find that answer. What is the local stiffness matrix for a member? Copy. And paste it here. What is the local stiffness matrix of an element? So now, when we talk about stiffness matrix for an element, we can have a frame member like this, okay? We're talking about the local stiffness matrix. So what's the local stiffness matrix? It's P equals KU, all lowercase. What does this mean? This stiffness matrix is the relation between the local forces at the nodes with the local displacements, okay? So it's all, this equation is all in the local direction of the element, okay? So here we have degrees of freedom, okay? We have a local degree of freedom in the local direction, in the direction of the member. The second one is perpendicular to the direction of the member. The third one is a rotation here. And then at the far end here, we have 4, 5, 6. Right? So in the local direction, we have 3 degrees of freedom per node here. We're talking about the local direction. Okay? Let's compare those 3 local degrees of freedom per node with what we had in frames and trusses. Sorry, what we had in beams and trusses. In beams, we had those degrees of freedom, the vertical displacement and the rotation, right? In trusses, we only had an axial displacement, right? Now we have all 3 combined. So actually K will be a combination of what we had for frames and trusses, okay? So the truss, the stiffness matrix for frame, the stiffness matrix for a frame member is a combination of those of the beam and the truss. So let's see how it's a combination of that. K, it's going to be 6 by 6. 1, 2, 3, 4, 5, 6, 7, and 3. Let's have this as large as possible. So here, it's 6 by 6. 1, 2, 3, 4, 5. 6, 1, 2, 3, 4, 5, 6. What are the numbers here? Those are the stiffness coefficients relating the forces at those degrees of freedom, at those 6 degrees of freedom, to the displacements at those 6 degrees of freedom. The first degree of freedom is the axial one. Okay? Here, we have to understand a very important thing. What's that? There is no interaction, there is no coupling between the axial displacement and the vertical and the rotation. Okay? What does this mean? If there is a force in the axial direction, that will never result in a force. If there is an axial displacement, yes, in the direction of the member, that will never result in a force in the, normal direction or a rotation. Okay? So that means that here on the first row, you're going to only have number at the first and the fourth, because those are in the direction of the member, okay? And we already did this for the trusses, okay? Remember how much were those numbers? It was EA divided by L. Applying a displacement in the direction of the member, the force is going to be EA divided by L, right? So here you have EA divided by L, negative EA divided by L. And here for the fourth, you're going to have negative EA divided by L, and EA divided by L. And then the rest are zeros. Why zeros? Because there are no coupling between the displacement in the horizontal or the axial direction of the member and the displacements in the normal direction to the member or the rotation. Those should be zero. There's no interaction between those forces and displacements. Okay? Now, for the second and third degrees of freedom, this is the vertical displacement or the normal displacement perpendicular to the member, and the rotation. What is the interaction here? We did this, those were what we had for a beam element, right? Those were what we had for a beam element. So I'm just going to copy those elements from the beam's stiffness matrix, okay? You remember, if you have your lecture note, just open the part for the beam. What was the numbers for the stiffness matrix for the beam? Do you have that? The element stiffness matrix for a beam. Twelve EI divided by L cubed, and then 6 EI divided by L squared, and then negative 12 EI divided by L cubed, 6 EI divided by L squared, and that should be symmetric. And then here you have 4 EI divided by L. And here you have negative 6 EI divided by L squared. 2 EI divided by L. Negative 6 EI divided by L squared. 2 EI divided by L. 12 EI divided by L cubed. Negative 6 EI divided by L squared, negative 6 EI divided by L squared, 4 EI divided by L. That's K. That's the stiffness matrix in the local direction for a frame member. This is very important. This is in the local direction. That gives you the forces in the local direction as the multiplication of that stiffness matrix multiplied by the local displacements. Okay? Everything is local here. Okay? So that's K. That answers our second question here. What was the local stiffness matrix for a member, for a frame member? Now, to answer the third question, it's going to be so easy. Okay? What was the third question? If we know the local stiffness matrix for the element, if we know the transformation matrix, what is the global stiffness matrix for the element? Okay? So let's come here and paste that. What is the global stiffness matrix? So as we did in the truss, what's the local stiffness, the global stiffness matrix? It's the same equation, P equals K U. But everything here is in the global direction, so I'm writing everything in the uppercase to differentiate between the local direction and the global direction. We use the lowercase for local direction and uppercase for global direction. So now I need to know how much is that K that relates those global forces to the global displacements. Okay? How can I do this? I know that starting from that equation, P equals KU, but in the local direction, okay? This is in the local. I know P small, P lowercase, is the transformation matrix multiplied by P in the uppercase. K remains the same. U is T, U uppercase. Right? So P in the global direction just going to be T inverse or T transpose multiplied by K T U. If this is equation 1, this is equation 2. So comparing equations 1 and 2, you would realize it's so obvious here that this K is just equal to that part. So K in the global direction is just T transpose K T. We know K in the local direction, we just had this here. Okay? We know the transformation matrix, we just wrote what's the transformation matrix, so you find the transpose of the transformation matrix, you multiply it by K that we had here, multiplied by T, you get K in the global direction. Doing so, that's what we're going to get. Okay? So K global is going to be equal to the following. How big it's going to be? Yes, 6 by 6. 1, 2, 3, 4, 5, 6. Okay? So it's 1, 2, 3, 4, 5, 6. No, 6. Okay? So it's going to be 6 by 6. What are those? What does those 6 numbers relate? Those are U, X, capital or uppercase at the near end, U, Y at the far end, at the near end, theta at the near end, u x f u y f and theta f. Okay? So that's what we're going to have here. Let's the numbers that we're going to have here, so complicated. I'm just writing it here for your reference. Sorry, the negative here is outside the bracket. Okay, negative EA divided by L minus 12 EI divided by L cubed multiplied by CS, negative 6 EI divided by L squared S EA divided by L minus 12 EI divided by L cubed CS negative 6 EI divided by L squared S negative EA divided by L C squared plus 12 EI divided by L cubed S squared negative EA divided by L minus 12 EI divided by L cubed CS negative 6 EI divided by L squared S. And then the second row here is EA divided by L S squared plus 12 EI divided by L cubed C squared 6 EI divided by L squared C negative EA divided by L minus 12 EI divided by L cubed CS minus EA divided by L S squared plus 12 EI divided by L cubed C squared 6 EI divided by L squared C, and that's symmetric. So 6 EI divided by L squared C negative EA divided by L minus 12 EI divided by L cubed CS minus EA divided by L S squared plus 12 EI divided by L cubed C squared. It's symmetric. I'm just copying the second row in the second column here. Okay? So that means that on the test, once you find the elements in the second row, you just copy them in the second column to, make things easier. 4EI divided by L, and then 6EI divided by L squared S, negative 6EI divided by L squared C, 2EI divided by L. That's going to be the third row here. So 6EI divided by L squared S, negative 6EI divided by L squared C, 2EI divided by L. And then the fourth column, that cup is here, EA divided by L, C squared plus 12EI divided by L cubed, S squared, EA divided by L minus 12EI divided by L cubed, CS, and then 6EI divided by L squared S. EA divided by L minus 12EI divided by L cubed, CS, 6EI divided by L squared S. And then the fifth row reads like 6EI divided by L, S squared plus 12EI divided by L cubed, C squared, negative 6EI divided by L squared C. And that is symmetric with the fifth row column. And then here it's 4EI divided by L. What do you think? You were asking about my personal life. When I was a student like you, okay, I did my undergrad not in the US, okay, I did that in Egypt.
Did you have to
Okay.
memorize this?
You are not allowed anything on the test, okay, and there is no equations given, there is no help from the professor. You have to memorize everything, every piece of information that you would need. What do you think?
I would drop. I'd find a new major. How long did it take you to memorize all this?
No, I didn't memorize it.
Oh, what'd you do?
Made a cheat sheet.
No. You're not allowed anything on the test. I never cheated, okay? So, but I didn't memorize this, and I got A in that course, okay? So, I just memorized the T matrix, the transformation matrix, and the K matrix, because that was easy, okay? That one is so easy to memorize, okay? And then on the test, once I found this one in numbers, and then the transformation matrix in numbers, I just did the multiplication. I didn't memorize it. I cannot memorize this. Okay? But you're luckier than me. I will give you that on the test, okay? You don't need to do the multiplication. You don't need to memorize it, okay? No one can memorize this, and I don't want you to make the multiplication, okay? I did the multiplication on the test, okay, so that I don't memorize this, okay? So that's the K in the global direction, okay? Now, everything else is the same, okay? The steps are the same. What are the steps? First, you find what are the degrees of freedom. You label your degrees of freedom, give notation for the members, for the degrees of freedom, for the nodes, okay? And then find K in the local direction if you want. You're not going to need that, but you find K for each member in the global direction through this matrix. What's C and S over here? Cosine and sine of theta. What's theta? Theta is the angle from the global x-axis to the global y-axis. To the global, x-axis. From the global x to the local x, okay? So that's C and S. E is the modulus of elasticity, I is the moment of inertia of the section, A is the area, L is the length of the member. Okay? So those are the things that you need here to put in this matrix. Okay? Once you find K for each member, what's the step 3? Find the K, the overall stiffness matrix for the entire structure. You combine this into the K for the overall stiffness matrix, K for the structure as a whole. And then you find P, the load vector, the displacement vector, and then write the stiffness equation. P equals KU, and solve for the unknown displacements and solve for the unknown forces. Right? Okay? That's the steps that we did so far. Okay? So the steps are the same. The stiffness matrix look different. Okay? For each of the 3 structures that we are studying. The steps are the same, the difference in the stiffness matrix for each member. The beam has a different stiffness matrix than the truss, than the frame. Okay? So now let's see an example over here. So I want to ask you a question before we continue. In your calculator, you can store that matrix, right? Can you store? Okay, check that, okay? When I was your age, I took that course in 1999, okay? Our calculators, we were not allowed any fancy calculators, okay? Just a calculator with a sine and cosine, that's all. So you can store that, okay? So please go ahead and store those, okay? Values, the K, okay? And I guess you can just, put E, how much is E, how much is I, how much is L, and it's just going to give you the numbers, right?
No.
Just check if your calculator can do this.
What if our calculator can't?
Huh?
I said, what if our calculator can't?
Okay, just substitute yourself. I'm allowing you, if your calculator can just, you can just store this matrix, with the variables E, I, L, and then you just substitute what's the value of I, what's the value of E, what's the value of L, okay, what's the value of C, S, and then it gives you the numbers. That will make your life easier, okay? So let's see that example over here. We have a frame that looks like this. Just 2 members, A, B, C. The distances are as follows: 20 feet, 20 feet, and 15 feet. Three kips per foot of load here, and those are all of the loads in that member. So here, when you're going to go on building the P, the load vector comes from the load at the degrees of freedom. Here you have intermediate loading on member BC. How you deal with the intermediate loading? You learn how to deal with the intermediate loading when dealing with the beams, right? So we're going to do the same thing, okay? It's not new, okay? We know how to deal with intermediate loading. E is 29 times 10 to the power 3 KSI. I is 600 inch per 4. A is 12 inches squared. Okay? So E and I and A. In that matrix that we just wrote over here, what else do you need to know? L and C and S. Why didn't I give you L and C and S? You can find them. L is the length of each member, okay? C and S are the cosine and the sine, so that changes from one member to another, so you just have to find that each member. So what we're required to find in this problem is required to calculate the reactions and the internal forces at B using the stiffness method. Okay. So we're not going to finish solving this example today. We're just going to do some steps, and then today I will let you go early. Okay? What's the first step? Annotation. So this is my frame. When I say my frame, what comes to my mind usually is if I own that frame. You know, I would be so rich if I owned that frame. Can you imagine how much steel in this frame? You know, if I can sell it, you know, that's a few $1,000s. Okay? So now I need to label that frame. Okay? The members, how many members do we have? 2 members. Okay? One member from A to B, the second member B to C. Okay? How many nodes do we have? We have 3 nodes. Node 1, node 2, node 3. So if you have 3 nodes, how many degrees of freedom you're going to have? 9. 3 degrees of freedom at each node. What are those degrees of freedom? Let's label the degrees of freedom. Okay? Let's draw them first and then label them. We said we have 3 degrees of freedom at each node. In what direction? Let's use the global direction. Okay? So a vertical, a horizontal displacement, a rotation at each node. A vertical, a horizontal displacement, a rotation at that node, a vertical, a horizontal displacement, and a rotation at that node. Okay? Let's draw it like this to be in the positive direction. So those are the 6 degrees of freedom, the 9 degrees of freedom that we have. Okay? We just now need to label them. How do we label them? We said you start labeling the unknown degrees of freedom. Right? Which of those 9 degrees of freedom are unknown?
B.
What about the degrees of freedom here? It's fixed, right? So everything is constrained, is resisted, is prevented. All the displacements here are prevented from happening, okay, because of the fixed support. You have fixed support here as well, so everything is prevented here. So the only allowed degrees of freedom to happen is those at B. So I'm just going to go and label those at B. So label them first. So you have 1, 2, 3. Okay? What? About what? Oh, okay. So 1, 2, 3. Okay? And then you label the unknown degrees of freedom. You can label them any way. That's 4, 5, 6. That's what I chose here. 7, 8 for the vertical, and 9 for the rotation. So those are the notations that we chose. So here, how many members do we have? 2 members. So you're going to need to build 2 element stiffness matrices. You have 3 nodes. That means that you have 9 degrees of freedom. What are those 9 degrees of freedom? 3 are unknown out of those 9. What are those? those, the first, the second, and the third are unknown, and those represented u, x, b, u, y, b, and theta at point B. And you have 6 known displacements, which are the 4th, 5th, 6th, 7th, 8th, and 9, and those are u, x, a, u, y, a, theta, a, u, x, c, u, y, c, and theta, c, and all of those are equal to 0. You have a support, so it's 0.
Capitals.
Hmm?
So these capital X and Y.
Yeah, capital. Those are all in the global direction. Okay? When you study the frame as a whole, you have only one option, which is the global direction, because which direction you're going to work with? Just the global direction. Okay? You unify all the directions into one global direction, and that's what you're going to use when you study the frame as a whole. When you study just the member, you have the option whether studying that member in the local direction or the global direction. Okay? So those are the degrees of freedom. What's step 2? Okay? What's step 2? The member's stiffness matrices. Members stiffness matrices. In what direction? In the global direction. So let's see here. For member 1, to write the member stiffness matrix, we need to know its length. The member was like this. The horizontal distance was 20 feet. The vertical distance was 15 feet. So the length, how much is the length? Square root 20 squared plus 15 squared. So that's 25 feet. So that's the length of the member. So L is 25 feet. To write the element stiffness matrix, what else do you need?
E, A, and I.
E, A, I, you have all of those. What else do you need?
Theta.
C and S. So C and S is cosine and sine theta. What's theta? The angle, okay? From the global X. Where's the global X? That's the global X. To the global Y, to the local X, okay? What's the local X direction? What's the direction of the member? It can have one of two directions, either this way or that way, right? What's the difference? It depends on how you choose to, label the nodes. Where's the start and what's the end of the member? If you say this is the start of the member and that's the end, so the member has that direction. If you say this is the start and that's the end, so the direction is in this way. Okay? So here I'm going to say that starts at node 1 and ends at node 2. So that means that this is the direction. This is the local X direction. Theta is measured from the global X to the local X. So that's theta. So how much is theta? I don't need to know how much is theta. I need to know how much is cosine theta and how much is sine theta. So cosine theta, how much is cosine theta? 20 divided by 25, right? So cosine theta is 20 divided by 25, so it's 0.8. How much is sine theta? 15 divided by 25. So that's 0.6. Okay? Now, if your calculator cannot substitute those numbers for you, as you see here, all the numbers that you're going to have is EA divided by L, 12EI divided by L cubed, 6EI divided by L squared, 4EI divided by L, and 2EI divided by L. And then they are repeated in combination with each other. Okay? So my calculator is not fancy. Okay? Cannot do this. I don't know if your calculator can do it or not. So I'm going to do it the difficult way. I have to calculate each of those parameters. EA divided by L. E is 29 times 10 to the power 3 KSI. Okay? Multiplied by A. A was 12 inches squared. Divided by L. L is 25 feet. Now, are those units consistent? Not. Definitely not. You have here K. Okay, you can leave the load in kips, that's fine. But for the dimensions here, you have those in inches and you have this in feet. So you have either option. You can change the inch to feet or change the feet to inch. So here what I have is changing this 25 feet to inches. So I multiply this 25 feet by 12 inches per foot. And now this number is going to be 1,160. And what's the unit? Kips per inch. Okay, you have here kips, KSI is kips per square inch multiplied by inch squared. So those inch squared cancels with those inch squared. And here you have inches here, so it's kips per inch. Okay? So that's EA divided by L. Now I need to have consistent units. I chose kips and inch, so everything else has to be in kips and inch. Okay? So 12 EI divided by L cubed is going to be 12 E, 29 times 10 to the power 3 KSI. I was 60 inches power 4 divided by L cubed. It's 25 feet cubed, right? L cubed. Those 25 feet, I need to change them to inches. So changing those to inches, you have 12. You have to multiply it by 12 inches per foot. And everything here has to be cubed. Okay? The length in inches has to be cubed. So that's going to be 7.73 kips per inch. Why kips per inch? You have kips per square inch here, multiplied by inch to the power 4, so that you have kips per inch squared, and here you have kips inch square, and then here you have inch cubed, so it's going to be kips per inch as well. Okay, so that's 12 EI divided by L cubed, and then 6 EI divided by L squared. So 6 EI divided by L squared and then I square all the length after changing it to inches. That's going to be 1,160 K. Okay? The units are important. 4 EI divided by L. You can just divide this by 6 and multiply by 4. Sorry. And then multiply by L. That's going to be 1,160 K. Sorry. It's going to be 232 times 10 to the power 3 kips inch. And then 2 EI divided by L is just 1/2 that value, so it's 116 times 10 to the power 3 kips inch. So now I can go ahead and build K1, the stiffness matrix for element 1. How large that's going to be? It's going to be 6 by 6. Okay? 6 by 6. Just substitute those parameters that we just found over that very nice matrix. Okay? Just substitute those here. You know how much is C, you know how much is S. You found all the parameters here. Just substitute them one by one. That's going to be 745.18, 553.09, negative 696, negative 745.18, negative 553.09, negative 696, 553.09, negative 696, negative 745.16, negative 553.09, negative 696. Symmetric, the first row is equal to the first column. And then the second row, 422.55, 928, negative 553.09, negative 422.55, 928. 928, negative 553.09, negative 422.55, 928. Third row is 232 times 10 to the power 3, 696, 928, negative 928, 116 times 10 to the power 3, and that's equal to the third column. And then the fourth row is 745.18, 553.09, 696, and that's equal to the fourth column. The fifth row is 422.55, negative 928, negative 928, 232 times 10 to the power 3. Now, what do you need to do? Label it. How would you label that member? You have to memorize this, okay? This is something you have to memorize. The arrangement of the degrees of freedom. How it's arranged. X, Y, and theta at the near end, and then X, Y, theta at the far end. So how it's labeled. X, Y, theta at the near end. This is the near end. So 4, 5, 6. 1, 2, 3. Okay? Four, 5, 6, 1, 2, 3. 4, 5, 6, 1, 2, 3. That's K1. Okay? You want to do the same to find K2. We can leave this for next time. K2 will be much easier. Why? It's already in the global direction, so actually K in the local is the same as K in the global, okay? So it's that matrix that we wrote in the local direction, okay? There is no transformation, so it's even if you use the global direction, many of the terms were just going to be, 0. You're going to have C equal to 1 and S equal to 0. So anything multiplied by S is just going to cancel. Okay? Any question? Which one?
The homework we just turned in.
No, what I will have you to do, the TA is going to grade them, and you can stop by the TA's office and pick it up by Monday. Okay?
Where's the TA's office?
You know that lab just beside the structural lab?
The asphalt lab upstairs.
Okay.
After the biology lab upstairs.
It's just next to my room. Yeah.
Just under.
Yeah.
So Monday and Tuesday we do not have class, right?
Monday, the Monday is for the concrete. So Tuesday there is no class for the structural analysis, and then Thursday you're going to have the test. Okay. And for the concrete, Monday you're not going to have a class, and Wednesday you're going to have the test. Okay.
And then Friday we have class.
Friday you have a class.
We don't have to have class if you don't. If you want to just take the whole week off.
Yeah, I wish.
I'll still turn your homework.
Dr. Gott, will you be in your office come after this class? Okay, I was going to work on mine. Hopefully try and work on my bridges.
Okay, sure.
You missed our study party last night till like 12 o'clock.
It's like we've been missing opposite classes.
Dr. Regal, what
Yes.
chapters did you say are going to be on the test? What chapters are going to be on the test?
In the email I sent yesterday, I said there will be beams using the matrix structure analysis and frames using the slope deflection method. So just figure out what chapters are those.
Should have done that better. I thought this was going to be on the test. I thought this stuff was going to be on the test. I'm sitting here stressing.
No. Just beams.
Yeah. I get it now.
The final, you're going to have those on the final.
Morning.
Morning.
Dr. Gall, were you still accepting homework?
I should not, but I will.